Hello guys, welcome back to another video. Today we're going to be doing a fun problem. As you can see here, we have x to the x is equal to some number a. Today we're going to be finding the solution of what x is truly equal to. So, immediately, let's take a look at this equation. On one hand side, we have both x in the base and the exponent. And right here we have a constant. So it's good to observe things first before we dive in. First things first is we can't really take the square root on both sides, because if we do, we have x to the x over 2 is equal to x, or square root of a. And that doesn't really get us anywhere, because we're trying to solve for x and isolate it. So what is something we can turn to? Well, first off, maybe there's another way we can represent x to the x. Let's take a look. X to the x. Let's see if we take ln on both sides. Always a handy trick if we want to reduce our exponent into a coefficient. So now we get x ln x is equal to the natural logarithm of a. If we rewrite this a little more, we can see ln of x times e to the ln of x is equal to the natural logarithm of a, just like that. So the reason this works is because e and ln cancel, so we're left with x, and that becomes x ln x, which is just the same right here. So these two expressions are still equivalent. It's just another way of writing it. So what's the whole point of this? We just got here where we have something. We can write this as u. So we let u equal to natural logarithm of x. That means we have u up here as well. So what do we just do? We can rewrite this as u times e to the u is equal to ln of a. But there's a really handy function in mathematics. The Lambert W function is defined as such. The Lambert W of x times e to the x is indeed equal to x. So this magical function which we'll be using, it's a lot more complicated than this, by the way. It has multiple branches that have different outputs, and it has different meanings as well. But in simple terms, the formula is this. W of x times e to the x is equal to x. It's the inverse operator of this. So we can apply the same rule here. If we take the Lambert W on both sides, just like this, we see now that this just outputs us u. So we isolated u, which is in terms of x. So let's see what's on the right side. U is equal to the Lambert W of the natural logarithm of a. Very simple. But what was u? We defined u to be ln x. So we can write this in terms of x now. We have the natural logarithm of x is equal to the Lambert W of the natural logarithm of a, where a was our arbitrary constant that were provided. So how do we isolate x from here? Let's see. On both sides, we can just exponentiate, because that's how we cancel ln. Earlier, we noted that we can rewrite x as terms as e times e to the ln of x. So we know that these are inverse operators. So all we have to do now is just exponentiate both sides with an e, like this. So now on both sides, this cancels. We have x is equal to e to the w, or Lambert W function, of the natural logarithm of a. So that's it. We have our definition of what x is now, and we've solved the original equation. But we can go further. Let's take a look. So now we solve this equation, but let's take a look now. In mathematics, if you did not know, there's a fun fact that I to the I, the square root of -1 to the power of the square root of -1, is indeed a real number, which is extremely shocking. But if you want the quick proof for that, we can analyze that. If we write this in a different way, we can write this as e to the I pi over 2. Because graphically speaking, if we look at the real and imaginary axes, if I label this, and this is the imaginary axis, and this is the real axis, I have a point here. This point, this is 1i, essentially. And we represent this by this angle. This angle in radian form is pi over 2, and there's so much more rigorous proof to this, but this is the simple way of thinking about it. And the way we write this is e to the r theta. So, this is r e to the I theta, just like that. In this case, r will be 1, and our theta is pi over 2. because if we go here, we approach this point, and this point is I itself. So that's why I is indeed equal to e to the I pi over 2. Quick explanation, but I can do a more in-depth video on that later. So we have this definition of I is equal to e to the I pi over 2. If we raise both sides to the power of I, what happens? We have I to the I is indeed equal to e to what is this? This is now I squared pi over 2. But wait, the definition of I is the square root of -1. So I squared is -1. So we have I to the I is equal to e to the negative pi over 2. It's as simple as that. But this is actually a real number. We have no I here. This is all real. Every aspect about this is. So indeed, this number is approximately equal to 0.2078 7957635, and so ... and it goes on and on and on. But if we just take a look at this number, we can use our formula now to see another way of representing I. So let's take a look. As we said earlier, a solution to this equation is x is equal to e to the w of ln of a. So let's take this equation and let's apply it further. We said that x is equal to, or if we have x to the x equals a, x is equal to e to the w of ln of a. So if we replace x with I in this case, we know that I to the I, let me move this over here. We know that I to the I is indeed this number. I'll just write 0.207879 ... like that. We know that much, so let's try to solve for I using our new function. I is equal to e to the Lambert w of the natural logarithm of 0.207879 ... just like this, which is extremely cool, actually. And if we want to rewrite this in a different way, we can just do I equals e to the w of ln of, what was this again? This was I to the I to the I. Just like this. And remember, with logarithms, we can bring this down as a coefficient. So, ladies and gentlemen, we have I is equal to e to the Lambert w of I ln of I. Now, if you take a look, we have the natural logarithm of an imaginary number. And this is a proof for another day. Stay tuned for another video. Thank you guys. See ya.